Today we'll be talking about group velocity and sorry, group velocity, and there will be more as well. Then we have stationary phase approximation. Stationary wave or phase, sorry, approximation. Approximation. Now, so pardon. So first of all, when we talk about the group velocity, the definition of group velocity is the speed at which the envelope, the envelope, the envelope, sorry, the envelope, we'll talk more on that later on. The envelope of the wave packet, propagate, propagate through space. That's what the definition of wave packet is. Sorry, wave velocity is. Now, um, in terms of equation, we can write wave group velocity as v of g is equals to dw over dk. Now here, this is, we know the group velocity, group velocity, and this over here is the angular frequency, angular frequency, and this is our wave number. Okay, now, but we can give an overview of envelope. Where envelope is, it's nothing but a smooth curve that outlines the amplitude variation. So basically, we're talking about wave as if we're talking about, we're more interested in its amplitude and its frequency, but in terms of quantum mechanics, not classical physics. Now, what the focus is on is the wave packets which are localized. Localized mean they have the effect is within the range, or which are localized particles or signals, and their movement through a dispersive medium. Movement, movement through dispersive medium. Now, this is group velocity in terms of dispersive medium, but in non-dispersive medium, persive medium, what do we have? We have velocity as Vp is equals to W over K. That's how our velocity will be. And the difference in this, what this velocity is famous, is that if our frequency changes, wave packets will spread more. Wave packets spread more means the higher the frequency, the higher the wave packet spreading. means more spread from here till here. Now, uh, then we have something known as stationary phase approximation. It's not like that. There's not that much information for the wave group velocity for now. So we'll just focus on the simple terms about what group velocity is and what is this equation. Wait, what? What is this equation? And it's this equation is for non-dispersive medium, and group velocity as of this one is this. By the way, d stands for the first order derivation, first order first order derivation derivation derivation. Now SPA, I'll just name it a short form so I don't have to write the full thing. Stationary phase approximation, which is a method. It's a method, by the way. It's a method used in asymptotic analysis. Sorry, method used in asymptotic analysis. Okay. Now the equation which is for this equation is I is equals to, let me change the color. The equation is I is equals to integral, oh sorry, it's just way too big. Integral of a of k e to the power I sis k over h bar dt. Now here, this part of the equation is the slowly varying amplitude function. Okay, function. And this guy over here is the rapid, not the full, this part is rapidly varying. This was an amplitude function, this is a phase function. Okay, it's a phase function. Now if by the way, for the wave, if we have this wave, this is the amplitude, or if there is one more way to write amplitude, this, and this to this, if they both are in the same degree of angle unit, then they have the same phase. That's what the phase is all about. Phase from a circle, like this is 90 degree, and with respect to circle, what phase we are looking at, that's the phase. Phase is for the comparing that wave in terms of circle degree, and yeah, that's what phase is actually in short, I mean simple terms. Now then this equation can also be written as, like, simplify, I mean if you simplify it, d of s k over dk. We're talking not this equation mostly, we're talking about this part, okay, which equals 0. It then again, this depends on h bar, which is, we know that Planck's sorry, reduced Planck's constant. Okay. And again, we are bringing back group velocity v of g, which is dw over dt. I think it was over here. Yeah, this one. Now we can now integral it to k, which is used for wave packets evolution. Now this equation is for the evolution of wave packets. Evolution of wave packets. Okay. Now, first of all, we talked about the envelope or the change in curve or curveness of the wave packet propagate through space. Then we are talking about the evolution of wave packets themselves. Now, how can we connect the stationary phase to group velocity? Well, they have a natural link. They have a natural link. Natural link mean they it's a by nature that they're related. Velocity and stationary phase. It's by nature, but they have some connection. Now it's written as Wt, again W is the angular frequency, T is time, minus K is a wave number, and X is the dimension we're looking at. This can be written as d over dx, sorry, not dx, dk where again wave number, then in brackets Wt minus kx equals to 0. Now this can further be simplified to give dw over dk equals to x over t equal to v of g. Oh, look at that. What do we got? X over t isn't the same as saying velocity is equals to distance, which is s over time. Oh, we just brought something which is classically. Now, reasons I just had to figure that show that comparison. Actually, twice. Now, reason for asymptotic limit in now this is the reason that asymptotic limit is there in group velocity. And so now then so then we have, let me give you a little bit view or the little bit about what is where is it again? Where did I lose it? Asymptotic analysis. Where is it? Where is it? Yeah. What is asymptotic analysis? Asymptotic analysis is a mathematical approach used to describe the behavior of functions as input approach a certain limit, often infinity as well. Now it's mostly used in computer science, mathematics, and physics. So, but here, of course, we're using for quantum physics. So we know we'll not go into depth of this, but there is one example in quantum physics. Asymptotic analysis is used in perturbation theory as well. That's one point. It's used in perturbation theory as well, but it's a method we use as a. We can also use it over here. Now, one last thing over here before we end, which is that how can we represent envelope or what I told is which is the smooth curve outlining the amplitude for variation function. How can we imagine it in terms of mathematics? Now what we can write is wave function, of course wave function is there when we talk about amplitude of wave packets, equals to a is some constant cos of k1 x minus w1t. This is how it's defined. You don't have to go to depth. You just but I thought you just had to know about the mathematical approach. Minus wt. No, that's not w. That's x. And this is 2. So this was k1 w1 and this is k2 w2. Now this is how the equation is. There's one trigonometric identity, metric identity, which is cos A plus cos B equals to 2 cos of A plus B over 2, and same as minus, or not minus, cos A minus B, this is opposite of what we got here. Now when we take this identity into common, what we see is that A cos A is this one and cos B is this one. So when we substitute, we get 2A cos, because A is common in both, 2A cos, and then K1 is common here, and K2 plus K2, or not K plus, minus K2 over 2, we are dividing it by 2, that doesn't change, x. So we're taking we're taking K as common here in terms of numbers, then minus. Now W, let's take W1 minus W2 over 2 K and X are not changing here. We are not doing anything to K and X. Cos, now before we did over here, as we did over here, K plus A plus B, then A minus B. So what we do here is it should be K plus K1 plus K2 over 2 X, and W1 plus W2 over 2T. I wrote it as, first I wrote the first one, means I wrote the negative and the negative first, and then the positive second, but you can do the opposite if you want over here as well. You could switch them as well. Now again, this part focuses on the slow, but what we talked about in this equation is this equation. Where is it? This one. Where do you go? Yeah, this one. This equation and this equation. This was the slow one and this was the fast one. Same goes over here. This is the slow moving part, slowly one, and this one is the rapid change. So this also shows that equation. Now further simplifying, we get our equation for the change in amplitude over time and space as e of x of t, e with respect of x and t, equals to 2a cos k1 minus k2 over 2x minus W1 W2 minus over 2t. This is our final equation in terms of amplitude. Yeah. So yeah, that's it. Yeah, and that's it. This is change in amplitude over time and space, which is x and t. Thank you.